distinguished sponsors, and distinguished guests. 7 years ago, Dr. Mueller, Dr. Nye, Dr. Schaefer, and I had the pleasure of participating in the predecessor conference of this one, and on the subject of radiations in outer space. I've recently had the occasion to review these papers. Now, I think there's nothing in these papers that should be retracted as being wrong, but they are shockingly obsolete as of the present day. So my task this morning is to undertake to give you a brief sketch of what we have learned in the past several years. Now, in the first place, I do intend to tell you and make as clear as I can some of the things which we believe are true, are established, and can be counted upon. Then I propose to mention a few of the aspects which are less certain, but have an element of truth in them, and to some extent can be trusted with suitable reservations. And then finally, I intend to say a remark on some of the things which we very much need to do and very much need to find out in order to make the picture more complete and more satisfactory.
Interesting that they should bring up this subject of confusion, because I'm not sure that after this lecture your minds will be any clearer with regard to meteorites in space. This subject, of course, is of critical importance to any operation in space, because wherever you go, you're going to encounter meteoritic material. The astronautical design engineer must first know the nature of the meteorites in space, their motions, their possible time variations, energies, and so forth.
Ladies and gentlemen, the task to give a comprehensive report about the electromagnetic environment of the atmosphere and the nearest space is somewhat difficult for two reasons. First, our knowledge of the state of affairs is limited to a very narrow skin around the Earth, narrow in comparison with the dimensions of the nearest space.
Mr. Chairman, ladies and gentlemen, the purpose of my talk is to present a preliminary model atmosphere based on rocket and recent satellite data. The basic data obtained are upper air densities. Since the densities evaluated from satellite data are the first experimental results which we have obtained at these great altitudes, a model based on this information may be justified, even if it will be realized that this model might have to be revised and improved when better and more data become available. In general, the densities obtained from satellite data are higher than had previously been assumed.
This afternoon, I'm going to restrict my presentation to the composition of the upper atmosphere above approximately 90 kilometers. My full paper deals with the composition at the lower altitudes, but I wish to restrict it because of time. I will further restrict my presentation to a discussion of data obtained directly by means of rockets and satellites. I feel the theoretical work has received adequate attention. These results are primarily on the composition of the upper atmosphere in terms of the major constituent gases, that is, nitrogen and oxygen and argon. This is not to imply that the minor constituent gases are not important or that they're not important below 90 kilometers. Quite the converse is true.
polymers of oxygen have been identified, but in traces only, and it is even possible that such polymers were created directly by the mass spectrometer itself. In the meantime, since Schönbein's studies, our knowledge of ozone has grown considerably. Since Sorey in 1860 found the chemical formula for ozone, definitely known as O3. The exact arrangement of oxygen atoms in the molecule, however, has been a subject of considerable investigation. Recent results indicate that the true structure of ozone is that of an obtuse model with an apex angle of approximately 127 degrees and a bond distance of 1.26 angstroms. A few properties of ozone may be mentioned here. It can be supercooled below its true melting point, about 55 centigrade, like glycerine, without undergoing solidification. The ferromagnetism of ozone is less than 0.1% that of oxygen.
The gravitational situation in space is usually described on the basis of the field concept. The introduction of the gravitational field concept has been an important mark in celestial mechanics and has proven extremely fruitful in research and teaching. It is a concept indispensable for the description of the mutual attraction of two or more celestial bodies, of perturbation of the orbits of smaller celestial bodies, of tidal effects such as ebb and flood, and many other phenomena. The gravitational field concept is and always will be the gravitational concept par excellence in astronomy, geophysics, and also in the fast developing field of astronautics.
Kilometer altitude, there is a vast region of space in which these new phenomena of a high radiation dosage do not prevail. And I think if we look at the development in the next 10 or 20 years ahead, this will be the region on which we have to concentrate. A globe-circling reconnaissance vehicle or passenger transportation over intercontinental distances with trajectory flight, to name only two important applications, these two will be carried out in the region below 1,000 kilometers, even only very likely in the lower half of this region. Therefore, I think we should not lose sight of the problems near at hand under the sensational impact of the new data, which will affect seriously the problem of flight to the moon or the flight to the Mars.
Mr. Chairman, ladies and gentlemen, during the past year, a new accelerator went into operation at the Lawrence Radiation Laboratory of the University of California. And for this year, some radiobiological studies were made possible. The name of this machine is the Heavy Ion Linear Accelerator, and it was constructed by Ed Hubbard and his collaborators.
Mr. Chairman, ladies and gentlemen, it is a great pleasure to be able to participate in this meeting. And I want, first of all, to thank you very much for having been thus honored. Within the limited time at my disposal, I shall communicate to you the results of research done for more than 6 years, together with Colonel David Simons of Holloman. The biological effects observed at great altitudes are caused by so-called nuclear radiation.
Thank you very much. Ladies and gentlemen, I'll make at least one correction to the introduction. It was not a sacrifice for me to come to San Antonio. I always loved coming back to my old hometown. The only trouble is I don't get the opportunity often enough. So I'm very happy to be here today, and I hope what I have to say will be of some interest to you. I'm sorry that Dr. Brock isn't here because that leaves me sort of holding the bag as chairman of the vehicles panel today, but I'll do the best I can to substitute for him, and I know that in that regard I'll be a pretty poor substitute. As already stated, my topic will be the weight limitations and capabilities in rocket propulsion for manned space operations. Now, I don't intend to get into very great detail because some of the speakers that follow me are going to discuss in greater detail certain aspects of what I will say in more general terms. Certainly, the major preoccupation of scientists in our time has been to understand and to unlock and apply the energy resources stored in matter. We would all agree, I think, that one of the most significant results of this preoccupation has been the discovery, the release, and the harnessing of energy for propulsion systems.
I think my paper really fills in a lot of the points which General Schriever has just been making. In this brief discussion on the matter, I'm not going to try and go through the whole of this paper. I'm just going to try and pick out some points which I think are of importance. It's customary, and I followed this procedure, to divide systems into high-thrust systems that are capable of operating from the Earth's surface, and low-thrust systems which must operate between orbits. I've not departed from that conventional procedure.
Mr. Chairman, ladies and gentlemen, the successful launching of the Sputniks, the Explorers, and the Vanguard satellites, and the recent launching of the first moon rocket, which accomplished at least the first phase of its flight successfully, have brought the space beyond our atmosphere definitely within our reach. The soundness of space projects in general has been demonstrated. The next major steps towards space exploration, the manned satellites, the lunar landings, and the planetary flights, may still be a number of years off, but almost everybody is convinced today that they will be achieved once their time has come. There is no doubt that a number of very serious problems must be solved before we can think of launching a vehicle for an interplanetary trip. We do not know yet how the materials on spaceships will react when they are exposed over a long period of time to the environmental conditions of outer space.
Thank you for your kind introduction, General Schriever. Ladies and gentlemen, you just heard from General Schriever that the Army and Navy and Air Force missile projects have many things in common. I think one thing that they all have in common is that long before the requirements and specifications can be spelled out in detail, one thing is sure, and that is the launching date.
Oh, it's broken.
Yeah. The launching date is well known long before we even know what the mission is. But there are a few aspects of a purely scientific and mathematical nature that govern the launching dates of both satellites and deep space probes. And I would like to talk to you a little bit about this rather timely item. And those of you who can put two and two together may even use this information to make an intelligence guess as to when the next chance for the moon will roll around. Let me first talk about the timing of satellites.
Mankind will not remain on the Earth forever, but in the pursuit of world and space will at first timidly penetrate beyond the limits of the atmosphere, and then will conquer all the space around the sun. This is an excerpt from a letter written in 1913 by Tsiolkovsky. The patron saint of the science of astronautics for the Soviets. The rocket-boosted glider is intended to accomplish this first timid penetration beyond the limits of the atmosphere. But such a vehicle may not only form the foundation for the conquest of solar space, but may always prove to be an essential part of any space system. In considering the rocket-boosted glider and its relationship to space, some significance can be attached to the historical development of the concept. This will be used to illustrate the fundamental system requirements appropriate to the glider and the significant design problems which appear.
Ladies and gentlemen, the subject of my talk is manned orbital and lunar space vehicles. Now, this is a very broad area. In view of the limited time, I would like to parade a number of principal points before you and have to refer to my paper for some of the supporting data. In order to set the basic frame of reference, I would like to say that if we by any chance would have a choice of the planet within the solar system from which we would like to start developing an interplanetary capability, I believe we couldn't choose a better one than the Earth. Because of the combination of Earth and Moon, a body with atmosphere, a satellite body of comparatively high mass, allowing us to operate almost through the entire system of flight profiles that we might later on encounter in interplanetary flight. And furthermore, train ourselves not only in coming down to a body with atmosphere, but also to one without atmosphere, which about covers everything that we would like to do in the foreseeable future inside our solar system. The development of manned spaceflight obviously begins in terrestrial space. That means the area in the immediate vicinity of the Earth.
Chairman, ladies and gentlemen, I think most of you realize that I was originally scheduled for this morning's program. I'm here a little bit, I think, in the nature of a guest star on television on a different program, I think, because today is probably a holiday and several of the speakers this morning were operating on a time-and-a-half basis. The calculation of the decelerations, which I'm going to talk about, which would be encountered by orbiting vehicles or space vehicles as they descend into the atmosphere of the Earth, is really quite simple in principle, but unfortunately it's a little cumbersome to obtain solutions to the general equations of motion. They're quite detailed. So what is usually done is to program simultaneous differential equations on a high-speed electronic computing machine and grind out numerical results. Now, a number of results have been obtained in this way. The procedure is to start with a specific vehicle in mind, starting at a specific altitude and entering some specific standard atmosphere. And since I believe that most of you here are familiar with a number of results of this type, I'm going to take a little bit different approach and first of all discuss the problem on the basis of an analytical approach, which enables us to see what the important variables are. And in order not to cover old ground here, I'm going to confine my attention to two topics. First, the decelerations involved with non-standard atmospheres, and second, and I think more important, a method of alleviating the rate of onset of deceleration.
Mr. Chairman, ladies and gentlemen, speculative opinion has been voiced upon many occasions that man is not ready yet for space flight because of some of the psychological and physiological limitations inherent within the human being. With continuing development of propellants and vehicle systems, it seems reasonable to assert that technical engineering ability will be of sufficient skill within the near future to place a manned space vehicle beyond the Earth's atmosphere. Before such a feat can be safely accomplished, however, much more must be learned of man's tolerance to certain of the environmental and other factors to be encountered in extra-atmospheric flight. Studies of many of these factors can, for the most part, be conducted in a static laboratory situation. Dr. Strughold has pointed out that after reaching altitudes of approximately 80,000 feet and above, the manned vehicle reaches a space-equivalent area in which a hermetically sealed cabin is a definite requirement. Consequently, the main laboratory instrument to be used to conduct experimental studies of this nature becomes such a cabin, properly instrumented for gathering data and for utilizing human subjects to perform tasks under conditions related to space flight.
Thank you, Mr. Chairman. I just wish I could live up to that introduction for the benefit of my children, if no one else. Some 4 years ago, at the prodding, or should I say the gentlemanly goosing of Professor Strughold, I prepared a preliminary analysis of the problem of what we call the photosynthetic gas exchanger for managing the gas exchange of humans in a sealed compartment. In considering the long-range problems of space flight, we have come to adopt a somewhat broader point of view as indicated by the present title. And in this larger framework, I should like to examine the rather meager present state of the art and the more pressing problems of development of this which face us.
As an integral component to perform the functions of monitoring, information processing, and decision making. For these higher order functions, man is well qualified. He is logistically manageable, has an unapproachable capacity for differentiation and decision making, and he can withstand environmental extremes with relatively little impairment of functional capacity. With qualifications such as these, prediction of reliability would seem to be an easy matter. But unfortunately, this is not so. And it is the purpose of this paper to review briefly certain psychological problems of space flight, which are most likely to seriously compromise the reliability of the human component.
Nominees, ladies and gentlemen, studies of sub-zero gravity have been directed toward the investigation of the effects of weightlessness expected to be encountered in future rocket flight missions as well as in satellite, and interplanetary space travel. These studies have involved the brief exposure of biological specimens, including man, to the weightless state utilizing parabolic trajectories of jet aircraft. In addition, ballistic missiles have been employed to yield longer periods of weightlessness for animal research, culminating in the Leica exposure of many days in Beta 1957, the so-called Sputnik 2. In the United States, research on weightlessness has been done primarily by the School of Aviation Medicine, United States Air Force, the Aeromedical Field Laboratory at Holloman Air Force Base, and at the Aeromedical Laboratory in Wright-Patterson Air Force Base, Ohio. Weightlessness up to about 40 seconds have been obtained during manned flight.
Mr. Chairman, ladies and gentlemen, this morning we heard requirements for new and exotic propulsion systems. For trips to the moon and for ultimate spaceships and perhaps refueling space stations, there were requirements that involve nuclear propulsion systems. The decision as to choice of propulsion systems, however, is more complex than just the consideration of energy utilization. Nuclear energy, as it is released, is a tremendous force, but coincident with its release is the emission of ionizing radiation. These radiations of varying energy can and do penetrate matter, the human body. It is important and imperative, therefore, that a real appraisal of the biological hazards, the dose effect, and the response to these various radiation sources be well understood if realistic permissible levels of exposure are to be determined. There must, however, be a careful balancing of potential radiation risk against the total benefits to be obtained.
Mr. Golan, General Todd, distinguished guests, and ladies and gentlemen. 7 years ago, at our first symposium in November of 1951, here in San Antonio, our interests were focused to a considerable extent upon the upper atmosphere, a region we then called the aeropause, and the region in which the various functions of the atmosphere for manned flight cease, and where the characteristics of space, such as vacuum, meteors, and cosmic rays, begin. This whole region, extending from about 10 miles up to the end of the effective or the appreciable atmosphere, around 120 to 140 miles, is also called the space equivalent region of the atmosphere. At that time, we discussed atmospheric space equivalence, a concept elaborated by Dr. Strookholt and his associates, which emphasizes that the conditions above the various functional limits are equivalent biologically to those in space. Despite the emphasis on the upper atmosphere and the borders of space, some papers at that time were truly astronautical data, did present astronautical data. Today, with the very rapid development of rocketry and the appearance of artificial satellites in the sky, the accent has shifted from the intra-atmospheric space equivalent regions into actual space or outer space. 7 years ago, with regard to speed, we had just broken the sonic barrier, and we dealt with the medical problems of transonic, supersonic, and hypersonic speeds. For the past several years, a new range of speed has come into the picture, namely astronautical velocities, with their two categories, orbital velocity and escape velocity. 7 years ago, we dealt essentially with the aerodynamic and aerothermodynamic problems involved in atmospheric flight. Today, our interests have been extended into the regions beyond the aerodynamically effective atmosphere, in which the laws of aerodynamics lose their meaning and the laws of celestial mechanics or astrodynamics are fully effective. In the first 50 years of human flight, we were concerned with extreme G-forces as they occur in crisis, particularly on the solid surfaces of the Earth. Today we have the same problems in a more complicated manner when a vehicle hits the denser layers of the atmosphere on re-entry from outer space. This second International Symposium on the Physics and Medicine of the Atmosphere and Space not only follows the first such assembly by 7 years, but antecedes by only 3 months the 10th anniversary of the founding of the Department of Space Medicine in the Air Force School of Aviation Medicine. We are delighted to have pioneered in space medicine and are pleased to be a part of the Air Force scientific family that initiated and significantly advanced the Man in Space program, a program of great interest to us since our concern is man. We are pleased, too, to announce to our colleagues in the physical sciences that aviation medicine, of which space medicine is really a logical extension, is an approved and accredited specialty ranking with the time-honored divisions of medicine. We believe that the great developments in astronautics aided us in obtaining this status and this professional recognition. Our thanks then to all of you. In speaking of the founding of the first organization in space medicine, it is of interest to point out that a physician, an astrophysicist, and a bioclimatologist were the members of the initial space team. This admixing of scientific talent was a logical sequel to the old flight surgeon engineer team who worked together for so many years. Now the School of Aviation Medicine, with its division of space medicine, has scientists on its staff trained in the following disciplines: medicine, space medicine, biology, botany, psychology, biometrics and mathematics, electronics, biophysics, radiobiology, microbiology, astrophysics, and engineering. We have additionally a number of skilled pilots working with us, many of whom have had scientific training. Now, the selection and training of people for our scientific team has followed a logical pattern in response to the intellectual challenges that confront us. There is nothing unique in our situation, because we find that the astronautical research teams throughout the nation, whether they be in industry, in universities and institutes, or in other governmental laboratories, are organized along multidiscipline lines. I was struck by a news account of recent date describing a major Air Force project in which it was stated that 3,000 people from 52 separate corporations or companies were involved, and that there was a great multiplicity and diversity of talent assembled to accomplish this particular program. It is apparent that there is taking place a progressive cooperation among men trained in the physical sciences, together with a growing association of men knowledgeable in the biological sciences. Quite obviously, the problems and the challenges of the conquest of space demand the full utilization of all of our scientific talent, and we are learning better how to blend and channel talent into the most productive research teams. In our first symposium, we did not include a discussion of the conditions found on other celestial bodies. In these days of lunar probes and equivalents, our interest of necessity is directed to other planets. All of these extreme conditions and the fact that we have to deal with a multitude of environmental factors, not only with the atmosphere, but also with gravitational, radiational, and magnetic fields, demand more than ever before in the history of human progress a very close cooperation between physics and engineering on the one hand and medicine and biology on the other. In medicine and biology, we use a terminology which is somewhat different from that used in physics and astrophysics and in the various technological fields. More than ever, the reasons for the intermingling of scientists representing all disciplines is apparent. In this symposium, we are again attempting to bring together the physical scientists and the engineers with the bioscientists in order to assemble all of the data pertinent to manned space flight. We wish to cement further our friendships and our scientific bonds, as well as to pool our knowledge. The first symposium introduced many of us to many of the leaders in the astro sciences, and possibly they to us. We desire to enlarge this circle of contacts for a more effective working rapport in the trying times ahead. It is our hope, too, to become far better acquainted with the scientific literature in other fields, and knowing the workers and the authors goes far to awaken and stimulate that greater interest. This meeting was essentially timed to come towards the end of the International Geophysical Year, because we wish to obtain all of the latest data that were being assembled from all over the world. We know of no better time, and we are excited over the large amount of completely new data that has been collated and will be presented. As always, we are interested in the environment of the astronaut and will devote the greatest amount of time to that subject. Our lecturers are preeminent in the field and come before us directly in most instances from field stations and laboratories. The national radiation of space will be a major subject, and discussions of simulation in the laboratory also of paramount and great interest. The question of vehicles for space exploration is currently a popular subject and merits much discussion. After all, it is the vehicle that will form the strange abode that lifts man into space and provides his every item of existence. It is the vehicle that propels him with exorbitant accelerated forces, and subsequently retards him with even greater stress. The bulk of the human problems stem from considerations of radiation and accelerative forces. We shall present pertinent medical observations that bear on spaceflight insofar as data are available. However, the interesting problem of weightlessness can be discussed from data observed only over very short periods of time, 1 minute or less. Discussions of the escape from a disabled space vehicle quite obviously must be theoretical and to some extent conjectural. However, it still remains a worthy subject for study and debate, and a small session will be devoted to this subject. In all, we have assembled here at this symposium much of the talent of this country with a sprinkling of outstanding scientists from abroad to pool our knowledge on an interesting array of subjects having to do with the conquest of space by man.
General Benson, our distinguished friends from the Western world, my fellow Americans. It is a high privilege and a very great honor to welcome such a distinguished group to the largest state in the nation south of the North Pole. Contrary to what some of you may have heard, Texas welcomed Alaska's admittance to the Union with open arms. We welcomed this outlying state because we were delighted that we had finally found a state that could outlie Texas. Gathered here tonight, all of us are in unaccustomed roles. I am, you might say, somewhat out of orbit, speaking to a scientific gathering of this imposing standard and quality. I should like to give you the opportunity to know some of my colleagues whose services I frequently claim credit for and who I always blame when something goes wrong. They're members of the Space and Astronautics Committee of the United States Senate and members of the staff of the Senate Majority Policy Committee. I should like for them to stand, and if you will reserve your applause if you're so inclined until all of them have been introduced, I shall be grateful. First, I should like to present Ms. Eileen Galloway and Dr. Glenn Wilson and Mr. George Reedy. And Now you really got something to applaud for, Mary Margaret Wiley. For you, it is not customary to sit and listen to one who comes from the political community rather than the scientific community. I know there's much you have to say to one in my position. And I want you to know that my eyes are open and my mind is open. I have in the past sought you out to ask your advice, your counsel, your interpretation, and your information. I'm sure that in the future I shall be doing this more often than I have in the past. Your counsel is needed and the need is imperative. It would be a mistake to regard the exchange of information and counsel between the scientific and political communities as just a one-way street. That is not the case, and I hope we'll never allow it to be so. For the age in which we live now, the political community of America also has some important things to say. Politics, in the highest sense of that term, is never obsolete. It has not been made obsolescent by our advance into the age of space. The technology of the space age demands of us a new breed of learned men. The politics of the space age, likewise, demands of us a new breed of politicians, a new brand of leadership, if you please. This is why I come to talk to you tonight. Americans, more than any other peoples on earth, have pioneered new frontiers. Each new frontier, from the New England shore to the California coast, has opened new horizons for commerce, for trade, for agriculture, engineering, and science. Yet in each instance, the greatest single effect has been upon our political institutions and upon our political concepts. The opening of the American West, for example, gave to freedom its American character and its American dimensions. It was in the vastness of the West that we lost the consciousness of class, the rigidity of economic position, and other such concepts which had lingered from our European heritage and tradition. Now we have arrived at a new frontier, the vertical frontier, as you call it, the space frontier, as the layman refers to it. You are the pioneers of this frontier. You are leading your nation and all of humankind into it, into a frontier so vast that it will never become settled and static and fixed. The space frontier is above all a perpetual frontier. Yet this frontier, like all before it, is not an end in itself. It is a means to an end, an avenue to the fulfillment of higher goals and nobler attainments than any we have ever known in the history of civilization. Your immediate concern is with the means to explore and to exploit this new frontier. The concern of the politician, the responsible public official, must be for the ends that ultimately will be served by the means that you devise and that you develop. This is your concern too, as Americans, as citizens of the world, as members of the human race. Will our adventure into the frontier of space enrich or impoverish the institutions of our political system? Will we, in reaching for the stars themselves, let fall from our hands the stardust of human liberty that we have managed to capture here on this earth? These questions need to be asked, and they deserve our closest attention tonight. What is our American purpose in space? What do we seek there? Shall we wander aimlessly among the stars and the planets and the galaxies of outer space, knowing not why we are there or what we seek? if our adventure into space is to have no more substance than this, it would be better for us 1,000-fold to abandon the quest in which we're now engaged and proceed no further along this challenging road. When a nation dedicates its resources and its capacity to any purpose, that purpose must have substance, or else the dedication is vain and the outlay of those resources becomes a waste intolerable. All of us know the philosophy of the celebrated mountain climber. Asked why he felt compelled to undertake to scale a most difficult and dangerous peak, he answered simply, because it is there. Among some Americans, it seems to me, there's a feeling that this is the philosophy of our adventure into space, that we're building satellites and shooting the moon and working on space stations, undertaking travel to the planets, and all of that for the simple reason that space is there. This concept is a fallacy. The holding of this concept is furthermore basically a disservice to ourselves and to our freedom-loving country. Americans, as I have said, have always been frontiersmen. Frontiers have shaped the character of our lives, our government, our principles, and our beliefs. We did not move into the frontier of the American West simply because it was there, nor because the Indians were there first. Men do not open frontiers casually. Neither do they pioneer out of fear. Men move into the unknown of a frontier because there's a compelling reason to do so. They are, I say, compelling reasons for us to move, and to move with greater force, and to move with greater determination than we have yet moved into the frontier of space. Security, of course, is a concern, an urgent and imperative concern which cannot be overstated. Obviously, the whole technology of warfare will forevermore be dominated by space weapons and space vehicles. If we had no higher interest and no higher national aim than merely to maintain equal capacity with the totalitarians, we would of necessity be forced to venture into space. But such are not and will never be the highest of our American aims. Security is a prime concern. It is not our whole concern or our sole concern. Security itself is not the reason. We are, as a nation, dedicated to the exploration of space. We are, as I see it, still a nation and a system of government, too young, too dynamic, too strong to give ourselves over wholly to the fears and the cares and the worries of an all-consuming concern for security. True, we live in anxious times. There is peril all about us. Yet the greatest of our perils is the prospect that we may allow our fears to transform our character, sap our vigor, and consume our strength. We have already seen this force at work. We have given over 2 decades of our lives and our times to security concerns, and we had no choice but to do so. We have, in consequence, accumulated a depressing burden of cost and debt and public taxation. We have consumed much of the vitality of our resources in this endeavor. We have reconstituted our industry to serve these ends. We have furthermore come to live closely with our fears. Fears of our capacity as a nation have been popularized. It has, in some quarters, grown fashionable to distrust the people with the truth and to impede the dissemination of public information. Others have grown fearful of free inquiry by free minds. All of this, I say, has no place in America. America is not made strong by its fears. Our strength is our confidence, not our doubt, our courage, not our hesitation. That is why I welcome our national arrival at the space frontier. That is why I so earnestly want us to press forward into it to move ahead and to seek what is there. As we found our national character in the frontiers of the American West, so I believe can we recapture our confidence and fulfill our greatness in the frontiers of the universe beyond the atmosphere. I do not say this idly. I say it soberly, and I say it with the deepest of conviction. It is my own belief that the first enemy of a free society and a free economic system is stalemate. A stalemate which forces upon us the wasteful consumption of our resources and depletes our energies for pioneering. We have existed in such a stalemate for a decade. The stalemate of East and West. The stalemate of great powers locked in contest for the minds and the souls and the bodies of humankind. We have not, until now, been able to see the end of this stalemate, except in the ruins of war or the decay and collapse of one economic system or the other. We could see an end, but we could not see for either side victory, for there would not be any. Now, though, as we stand at the edges of outer space, we can see both. We can see the end of this stalemate, and we can see victory. Not victory for one nation alone, but thank God, victory for all mankind. I do not understand your arts in detail, nor I suspect do you understand those of my pursuit. But I know, and I know that I know, that as you take us among the stars, men of politics and diplomacy will be able there to find the foundation at last for peace in the world. Peace is the first and greatest opportunity that space affords. But there's more. We cannot reach into space successfully without marshaling the full potential of our resources, and in fact, the resources of the entire world. This means for the first time that we shall summon up the ultimate of our capabilities, and by so doing, enrich the lives of us all. We shall not in our own country be able to afford the waste of neglected regions. We shall not be able to tolerate the wastage of our water and our soil and our forests and our minerals, or, more important, our reservoir of human minds. This is the real strength of America. Not guns and not tanks and not ships, not jets, not missiles, and above all, not fears or doubts or suspicions. This is the kind of America and the kind of world in which free men want to live, and free men ought to live, and free men can live. In a climate of growth and expansion, our economy can and will attain new heights of abundance and productivity. In such a climate, too, our democratic institutions of freedom can flower to new nobility and seed the world with their greatness. Men have never faced so exciting a challenge as we do now, tonight. We need, in both the scientific community and the political community, to understand this better ourselves and to foster that understanding among all those about us. We need, I believe, to end our idle lamentations about failures in our American system. I do not hold with those who have been quick to say that American education has failed, or that American parents are failures, or that business has failed, or labor, or the military, or particularly the men of science. One need only to look about himself to see plain evidence that the American people have not failed. Our justified self-criticism is not at what we have done, but at the narrow limits and the low standards that we have set for ourselves on what we were willing to try to do. We have, as a nation, done well most that we have tried. But our goals have been far less than our potential. We have chronically underestimated the power of a free economy. We have undervalued the human mind and its capabilities. We have underrated the people's capacity for wise and trustworthy decisions, and the people's ability and willingness to meet that challenge. Our need now is to overcome these errors, to stop selling ourselves short, and to undertake the fulfillment of both our promise and our potential. This is the direct and immediate challenge of the space frontier. It concerns us all. The nation needs from you a better articulation of the promise space affords and the potential that space holds. America needs from the political community a new brand of confident, courageous, pioneering, can-do leadership. The burdens on our economy, accrued through the years of stalemate, are best lightened by building a stronger, a bigger economy, and this must be our first concern. Likewise, growth, expansion, the equalizing of opportunities through all our regions represent the best hope for release of the tensions which divest our energies from the forward course. In a world circled by the vehicles of space, there can be no secrets. We need, therefore, to concern ourselves not with guarding what we know, but rather with exchanging and pooling our knowledge with all the community of free men. These things and more are both the opportunity and the obligation of this new frontier into which we're moving. We have before us the challenge of breaking the stalemate by which the world has been too long chained. We come to a time when America can and must take the offensive, not for aggrandizement, but for the fulfillment of the ultimate of the free concepts by which we live. These are the ends we seek, through the means with which you are so directly concerned. This is the American purpose out in space. We're moving forward, not aimlessly and not casually. We're moving to extend the frontiers of freedom, personal freedom, social freedom, economic freedom, and the freedom of liberation from war. With this potential within our reach, we must, I say, move forward with much greater effort, with much greater determination, and with much greater force. What we can attain makes worthwhile the investment of our resources many times over what we are now doing. The urgency of attaining it makes imperative the unshackling of our research from the bonds of old concepts and old jurisdictions of the past. We have made within the year a start in these directions. We have vested direction of our efforts in a new agency. We have committed ourselves properly to the higher aim of peaceful goals. We are proposing to our sister nations a full and joint cooperation in the exploration of this new direction, to which I will allude in somewhat more detail on next Monday at the United Nations in New York. These are gains, but they are only beginnings. As we learn more of this new age and these new arts, we must return again and again to the scrutiny of our patterns, not only in government and in the military, but in business and in the professions and education and industry. We must concern ourselves with achieving the fullest utilization of our trained minds. Where talents are hoarded wastefully, we must seek their redistribution to more productive labors, whether in the military or in industry. Where there is want for such minds and talents to teach others, we must strive to meet those needs. We must concern ourselves, too, with the processes to which our progress is entrusted, to make certain that the processes yield the very highest dividends. Our research dollars must yield research dividends and not be dissipated casually in non-productive channels of contracting which may now be obsolete. Certainly, we must find at the government level a way to reconcile the necessary prudence of handling the taxpayers' money with the necessary pioneering of pure research. These are concerns. Only a few of many that I could mention to you tonight, to which I hope the Space Committee of the Senate can give diligent attention next year and have the counsel of so many of your most distinguished men present this evening. In these efforts, we shall always welcome your guidance and shall ferret out and seek your counsel. The challenge I would emphasize is not to find fault and not to investigate errors and not just to fix blame. The political challenge is to lead, to manifest the confidence and the courage born of understanding that these times and at this age demand. Likewise, this is the challenge to the scientific community as well, to lead, to pioneer, to venture wisely and boldly, and to move forward as the frontiersmen of America's history have always moved forward. As you move forward, you must remember the human race follows on the trail that you will mark. Your responsibility is a very great one. My responsibility and that of all men in public life today is great also. America has placed much in our trust. We must honor that trust with the best that is in us. Thank you, good night, and God bless you.
Comprehensive program in basic and applied research on the entire complex of environmental factors that can affect humans during flight. I think all of us that are physicians or are in the biomedical fields are used to working with people all over the world in our particular specialties and have no particular trouble in communication. I might say that a lot of us that are associated with the latest NASA Man in Space program are very happy that Mr. Robert Gilruth is the project officer, so to speak, in charge of it, that the Army, Navy, and Air Force already have personnel assigned to Langley Field that are working full-time with him and his group. As time goes on, the crew, who will be carefully selected on the basis of experience, resistance to stress, such as acceleration and temperature, and after extensive training will be checked out in ground and flight tested environment, and everything possible will be done to ensure that they will be able to perform as they need to.
Thank you, Captain Newman, Colonel Neese, gentlemen. I tried to prevail upon Dr. Lovelace to do this entire thing, but he has the rather strange notion that when we talk about putting a man into space that a pilot might have a cursory interest in this occupation. We're a little hard put these days to wonder where we fit, particularly after an experience at Wright Field here several weeks back. They were running some tests on me to see if I would make a competent aviator, and on a device that was probably invented during the Inquisition, and they were talking about things of the nature you're talking about here today, and asked the aeromedical subject next to me if he would like to be a test pilot also, and he said, no, it's bad enough being a chimpanzee. Dr. Lovelace got us into orbit, and I've got 6.5 minutes to get us out. In orbit, the duration, of course, is governed by the desired landing site, if we're speaking of these initial attempts we're going to make. And if we launch in the United States and recovery is desired in the United States, then the duration that the man will be flying will be from about 1.5 to 4.5 hours, or about 24 hours with little choice in between if he wants to get back into the United States. Aeromedical problems in orbit, in my mind, in order of importance: boredom, zero-G, radiation, and then some of these invented difficulties of detachment and so forth. And this order is for the duration of hours.
Touch any buttons till you get me tied down. As Chief Inquisitor of this torture institution to which Mr. Crutchfield made reference, I would like to go into some of the problems which may help us to make it possible for a man following an orbital flight to indeed close a flight plan rather than to complete an obituary. Scott referred to chimpanzees. Among them, I have friends who would take issue with him and say it's bad enough being a man. I'm certain that all that has gone before will bear out the thought that only a scaling of experimentally demonstrated ballistic flight is required to accelerate the minimum mass for a manned vehicle into orbit or to escape velocity.
Places a man or a crew in the immediate vicinity of tremendous quantities of highly explosive, highly corrosive, and inflammable materials. Thus, provision must be made for instantaneous clearance from the vehicle to a safe area in case of launch difficulty. After launching, and while in the Earth's atmosphere, and in the course of relatively high degrees of acceleration, the situation is somewhat different, and possibly the basic escape mechanism requires some alterations to meet contingencies. Above the Earth's atmosphere, in the hostile environment of space, while at very high velocity, or possibly in orbit or ellipse, a situation is still different, as it is again during re-entry. A common denominator in terms of a single escape system to meet all of these requirements is at present difficult to perceive. Communications with Earth in event of difficulty is a problem within itself, as is location, course, and the mathematics of interception, if such becomes possible.
Thank you, Colonel Campbell. Good morning, gentlemen. 11 years ago, last month, man first flew faster than sound. Today, there are thousands of aircraft with this capability, and flights of well over 1,000 miles an hour are everyday occurrences. In existence at this moment are vehicles essentially capable of putting man in space. With only a little more assembling of proven components, the feasibility of orbital flight around the Earth by man is a foregone conclusion. It is not our purpose here today to debate the benefits to be derived or expected from carrying a human crew on flights into space. As a matter of fact, it can be shown on logical grounds that such a venture is both foolish and unwarranted.
Thank you very much, Captain Barr. Ladies and gentlemen, I'm up here again, and this time I try to be on time. The subject of rescue in space is indeed a very interesting one and a critical one. I made an attempt in 1948 to write a little novel called Expedition Ares, which I wanted to liven up by some realistic incidents, dramatize and so on. And when I started thinking about this, it occurred to me that I didn't know where to start with those incidents and accidents and failures and where to end. And was much tempted to write a book with a number of chapter titles of the type How to Poison Yourself with Propellants, Explosion During the Launching Site, Sudden Decompression Upon Entering Space, Lost Without Navigation, Crashing on Mars, and Cremating Yourself During Re-Entry, and similar things. But since I was for spaceflight, not against it, I decided not to write this kind of a book.
Mr. Chairman, participants, there's a little change in the title of this, and the title of the paper should read Rescue and Retrieve Space Missions. I would like to touch briefly directly from the text, then to proceed to the detailed information on the slides, and then as the time runs out, I would shift to the concluding remarks. The purpose of this paper is to consider one special area of escape and survival in space, that of rescue and retrieve of crews from malfunctioning orbiting vehicles. Emergency missions categorized as either rescue or retrieve involve two fundamental aspects of spaceflight mechanics: time and energy required for interception by either ground-based or satellite-based emergency vehicles. The paper presents 1, the emergency conditions; 2, operational problems of ground-based and satellite-based emergency systems; 3, the flight mechanics involved in giving minimum time or low time and minimum energy or low energy transfers between orbits; 4, coupling techniques at interception; and 5, interceptor design and maneuverability requirements.
Thank you, Norm. Fellow radicals, the space traveler who fails to survive the journey cannot realize adequately his desire for adventure and knowledge. Effort put into the safety and reliability of normal functions can often contribute much more to total effectiveness and survival than an equal amount of effort put into excessively complex or rarely applicable escape equipment. Experience has nevertheless shown that unexpected hazards or unpredicted combinations of factors result in a significant number of failures from which escape is the only course to survival. The large number of unknowns, together with increased complexity and energy of space vehicle systems, will probably increase the percentage of failures requiring escape.
Thank you, Mr. Chairman, ladies and gentlemen. For the first time in history, man is on the point of leaving his natural spacecraft, our Earth, on which we live more or less comfortable, by means of an artificial one. The expenditure for a manned satellite, which is quite a bit more complex than an instrumented satellite, can be justified only if man's physical and mental performance is fully utilized. Man will still be superior to instruments by his higher versatility, his ability to exert judgment and make decisions. On the other hand, the payload is restricted. The payload ratio to rocket is awful small, so we have to exert the utmost restriction in weight and volume, and still keep men at maximum top performance.
Dr. Baldes, General White, ladies and gentlemen. I shan't be so presumptuous as to discuss the mathematical formulation of the special and general theories of relativity. I don't know that enough about them. I should like, however, to ask some questions by posing problems. I shall not be able to answer most of these questions. Perhaps much of what I say will be considered pure speculation and conjecture, and I readily admit this. Much of this new science of space medicine, however, is speculation and conjecture, so perhaps my remarks are not so much out of place. Even plane geometry at one time was conjecture and even quite magical. However, engineers and biologists interested in space travel need to examine the theory of relativity to ascertain whether the formulation predicts any physical or physiological effects which might be of use in their respective scientific efforts.
The task of the high-altitude flyer and the astronaut does not require vision outside his cabin. It is performed on instruments. In a windowless cabin, indicators, dials, switches, and cathode ray scopes can easily be presented to his eye under optimal conditions of luminance, contrast, and resolution. For best visual results, he should be acclimatized to the prevailing oxygen content of the cabin. Under such conditions, visual performance should not differ materially from that obtained at sea level. Even then, however, human reaction times may be too slow for adequate control action. Lacking the scattered light from the sky, the illumination from the sun produces excessive contrast in a cabin. To avoid glare, clear windows are not desirable at extreme terrestrial altitudes and in space of distances up to 1.8 billion kilometers from the sun.
Mr. Chairman, members of the Symposium, about 25 years ago, Dr. G.E. Hale, the distinguished Mount Wilson astronomer, pleaded with his colleagues to begin taking photographs of the face of the sun more often than once a day. He felt that one photograph per day, as was then the custom, would miss many important changes of solar activity. Today, after a quarter of a decade, thanks to many developments, not the least of which is Dr. NICOLET's IGY, there has been a tremendous change in the completeness of coverage of solar activity. For example, there are over 100 stations that take throughout the world photographs of changes in activity of the sun. More than 30 of these take pictures every 3 minutes or more frequently, some every 30 seconds.
Chairman, ladies and gentlemen, I have selected a number of slides which I would like to use to illustrate the points which I would like to make. The Monday morning program has dealt already quite extensively with the space between the Earth and the Moon, so I believe I should not spend any time now to go over the particles and radiations which traverse space between the Earth and the Moon, and which, of course, influence very profoundly the planetary atmospheres in creating exospheres, spheres from which the planetary atmospheres evaporate into space, and, in fact, the surface structure of the Moon itself.
Mr. Chairman, ladies and gentlemen, the planning and successful accomplishment of an exploration of Mars will require careful consideration of the best available information on physical conditions on the planet and in its atmosphere. Our factual information of these conditions is still severely limited in spite of the voluminous literature on Mars. The basic data have been reviewed in a number of books, the more complete of which are the monograph by Antoniadi in 1930, The Atmospheres of the Earth and Planets by Kuiper, and possibly Physics of the Planet Mars. So I will concentrate today on main findings during the past 4 or 5 years since the publication of these books. I should like to point out right at the beginning that the remaining uncertainties are often very large. These uncertainties will call for caution and generous allowance for possible errors when applying such data to estimate safety factors in technological applications, especially when manned operations are considered.
The existence of life on the planet Mars has been the subject of much hypothetical discussion. Because of the nature of the problem, the hypotheses and theories which have been advanced have of necessity been based on one of 3 approaches: fantasy, a few direct scientific observations, and a few indirect studies. Many of the recorded hypotheses concerning life on the planet Mars have been based on an admixture of fact and fantasy, with more emphasis being placed on fantasy than fact. These presentations have made interesting reading, but have done little to advance scientific knowledge as to the possibility of life on the planet.
Chairman, ladies and gentlemen, when I was first approached to deliver this paper here, I was asked to present a summary paper rather than a specific paper on some detailed subjects. And as summary papers go, it has to be rather general in nature, and it probably will be a little bit too elementary for some of you here today. It is dealing with interplanetary travel that we're talking about. This is the stage beyond the unmanned travel in space. This is the stages where we try and take people with us to help in these adventures.
Chairman, ladies and gentlemen, the consideration of spaceflight from the viewpoint of the physician, of its possibilities concerning spatial extension and duration, is a difficult and a challenging task. But looking back now upon a 10-year-old history, space medicine can make some definite statements. These can be based on physiological theories, on medical evaluation of physical, astrophysical, and technological data, on basic and applied experiments in a simulated form in the laboratory, and on experiences in the field. That means in manned flight within the intra-atmospheric space equivalent regions by means of balloons and rocket-powered craft, and on animal experiments in actual space. Relying on these various approaches and methods of research, we have a complete knowledge about certain factors involved in spaceflight. About others we have some knowledge, and about the rest we depend entirely on extrapolations and even on speculations. Great contributions have been made by the papers presented at this meeting, which have provided an up-to-date information for the following review about the so-called state of the art in space medicine and its related field, astrobiology. I feel very honored to have been asked by General Benson, the originator of this symposium, to give this kind of paper.